We're diving deep today into a paper by Margaret Mitchell, Sasha Luccioni, and a whole group of other researchers.
Yeah.
It's called Measuring Data.
Yeah.
And it really gets at this question of how do we measure these massive data sets that are behind all of our machine learning models?
Right. It might seem kind of obvious,
Yeah.
like at first, but when you really think about it, we treat these data sets a lot of the time like black boxes.
Yeah.
We're always focused on making the models better, but the data itself is just sort of there.
And that's starting to change, right?
Yeah.
With data-centric AI, people are realizing that, the quality of the data, how it's characterized,
Yeah.
That can make or break a model.
Absolutely. And we're seeing all these new tools popping up like Clean Lab, Data Lab, that are really focusing on quality data curation. But this paper is arguing that what's really missing is a systematic way to actually evaluate and measure the data itself.
Oh.
They say we need a whole new science of data, which they're quoting from a 2021 paper by Sam Basavan and others.
So let's unpack that a little bit. What does it actually mean to measure data?
Right.
Are we talking about like measuring the length of a table or the weight of an object?
Yeah, in a way it is kind of like that.
Okay.
So just like we have units of measurement, for those physical objects, they're proposing this idea of data units.
Okay.
So this could be characters, words, images, whatever the basic building blocks of your data set are.
Interesting.
And just like we can measure height with depth of an object, they're saying we can measure data along all these different dimensions to quantify its characteristics.
So instead of just saying, oh, this data set is kind of sparse, you could actually say this data set has a data density of X.
Exactly.
I mean, that seems incredibly useful, right? For comparing data sets, for really understanding what you're working with.
Yeah, absolutely. And they lay out 5 main categories of data measurement.
5, okay.
Distance, density, diversity, tendency, and association.
Okay, so that's pretty comprehensive. Let's start with distance.
Sure.
How do you measure the distance between, like, pieces of data?
So think of it like we're plotting all these data points in some multidimensional space.
Okay.
And the distance measures tell you how far apart those points are.
Got it.
So the paper mentions a whole bunch of different distances, measures everything from like the familiar Euclidean distance to things like Kullback-Leibler divergence.
So you could use this, for example, to see how similar or different two images are, like based on their features.
Exactly. And they specifically talk about inception distance, which uses a neural network to measure the distance between distributions of generated images and real images.
Okay, so distance gives us a sense of similarity or difference. What about density?
So density is all about how tightly packed data points are in a certain region of our data space.
Okay.
So a high density area might indicate a cluster of similar data points, whereas a low density area could represent outliers or underrepresented categories.
I can already see how this would be valuable for things like anomaly detection or identifying gaps in your data.
Wow.
They list KNN density and data density as like general measures of density. Are there any that are kind of specific to certain types of data?
Yeah, for sure.
Okay.
So, for example, in natural language processing, there's idea density, which measures how many ideas or propositions are packed into a sentence.
Interesting.
So higher idea density often means more complex writing.
So a data set of academic papers would probably have a higher idea density than like a data set of tweets.
Yeah, most likely.
Okay.
And then in computer vision, we have image density, which tries to model the probability density function of images.
Okay.
So it's helping us understand the distribution of features within those images.
All right, so we've covered distance, we've covered density. What's next in our data measurement toolkit?
Let's talk about diversity.
Diversity seems crucial, right, for building robust and fair AI systems. How do we actually quantify that in a data set, though?
So essentially, it's about measuring the variety or heterogeneity of the data points. So a diverse data set will have a good spread of different categories, classes, or features.
So a facial recognition data set that only includes people with light skin tones would score low on diversity.
Exactly. And the paper talks about the Giant Diversity Index and the Venn score as general measures of diversity, but they also dive into some modality-specific measures.
I'm guessing there are some interesting ones for language and vision data.
Yeah, absolutely.
Okay.
So lexical diversity is used in natural language processing to measure the richness of vocabulary used in a text.
Okay.
And computer vision, there's the inception score, which evaluates how diverse the images generated by a model are.
Okay.
So a model that generates very similar looking images would have a low inception score.
So if you trained a model to generate images of cats and all the cats look identical, that would be a red flag.
Exactly. It would mean your model hasn't really learned to capture the full range of variation in cat features.
Okay, 3 down, 2 to go.
All right.
We've talked about how spread out data is, how clustered it is, how varied it is.
Right.
What's the fourth dimension we need to consider?
So think about the overall shape of the data, its central tendencies, and how those data points are dispersed.
Okay.
That's where tendency measures come in.
Okay.
So we're talking about familiar concepts like median mode, standard deviation.
Right.
But also some less familiar ones like burstiness and skewness.
Burstiness, that sounds intriguing.
Yeah, so it captures how often events kind of cluster together and bursts over time.
Okay.
So imagine you're analyzing social media data. You might see bursts of activity around a major news event.
Or if you're analyzing like stock market data, you might see bursts of trading activity during periods of high volatility.
Exactly. And then there's skewness, which tells you how symmetrical or asymmetrical the distribution of data is.
Okay.
So a data set with a long tail of outliers on the high end would have a positive skew.
Right.
And these tendency measures are super helpful for understanding how well your data actually fits certain statistical assumptions.
Right.
So for example, a lot of models assume that data is normally distributed. So high skewness could indicate that you need to transform your data before you even feed it into the model.
Makes sense. Are there any modality-specific tendency measures worth highlighting?
Yeah, so for language data, there's fit to Zipf's law,
Okay.
which measures how closely the word frequency distribution in a text matches Zipf's law.
Right.
And natural language tends to follow this law, so deviations from it could indicate interesting patterns or potential anomalies.
So if a text has an unusually high number of rare words, that might raise a red flag.
Precisely, it could suggest the text was generated by a machine or written in some very specialized jargon.
Fascinating. All right, we've covered a lot of ground here. Diversity, tendency. What's our final stop on this data measurement tour?
Association.
Yeah, it's all about understanding the relationships between different elements in your data.
Okay.
So we're talking about concepts like correlation and mutual information.
So if we're looking at a data set of customer purchases, we might find a strong correlation between buying diapers and buying baby formula. Exactly, because those items are often purchased together, so there's a strong association there.
Right.
And that kind of insight can be incredibly valuable for things like product recommendations or targeted marketing.
I see. So association measures help us uncover those hidden patterns and dependencies in our data. What are some of the specific measures mentioned in the paper?
So they talk about classic correlation measures like Pearson correlation and Spearman rank order correlation,
Right.
which quantify the strength and direction of linear relationships.
So a positive correlation means that as one variable increases, the other tends to increase as well.
Yeah.
Okay.
And they also discuss point-wise mutual information, or PMI, which measures the association between the specific terms or concepts.
So you could use PMI to analyze the co-occurrence of words in a text corpus.
Right. For example, PMI could tell us that the words artificial and intelligence often appear together, indicating a strong association.
Got it.
But it's important to remember that association doesn't always equal causation. Just because two things are correlated doesn't mean that one causes the other.
Excellent point. So we've now covered all 5 categories of data measurement.
We have.
It's a lot to take in, but I'm already starting to see how these measures could be incredibly powerful for, anyone who works with data.
Yeah, I think by measuring data along all these different dimensions, we gain a much deeper understanding of its characteristics, and ultimately that leads to better models, more informed decisions, and just a better understanding of the data itself.
This has been an incredible deep dive into the world of data measurement so far.
It has.
I feel like we've just scratched the surface, though.
Yeah.
There's so much more to explore in terms of the practical applications and implications of all these measurements.
I agree, we've laid the groundwork, but now it's time to see how these concepts translate into real-world results.
Exactly. So for those of you who are eager to learn more about how data measurement can be used to build better and more responsible AI systems, stay tuned for part 2.
Sounds good.
Welcome back to our deep dive into the world of data measurement.
Yeah, in this part, I think it's really interesting to start thinking about, shifting from what it is to why it matters.
Right.
Especially for, folks like us who work in machine learning.
Yeah, because at the end of the day, we want to build models that work and work well.
Exactly. And, so much focus has been on, the model itself.
Right.
Tweaking the algorithms, the parameters. But what if the bottleneck isn't the model, but the data you're feeding into it?
That's a great point.
Yeah.
So data measurement becomes a way to diagnose and maybe even fix problems at the data level before you even start building your model.
Precisely. It's kind of like a doctor, running tests before prescribing medication.
Okay.
You need to understand the patient, which in this case is the data set before you can treat it effectively.
I like that analogy. So
Well,
give us a concrete example.
yeah.
How could data measurement actually lead to better model performance?
Okay. So let's say you're building a model to predict customer churn. And you've got all this data on customer demographics, purchase history, website interactions, all that stuff.
Right.
But your model just isn't performing as well as you'd like.
So you could start measuring the data right along those 5 dimensions we talked about earlier.
Yeah.
Distance, density, diversity, tendency, association.
Yeah.
What kind of insights might that reveal?
So imagine you measure the density of your customer data.
Okay.
And you find this really low density cluster of customers who churn at an unusually high rate.
Interesting.
That's a signal that there's something unique about this group
Right.
that your model isn't picking up on.
It's like finding this hidden pocket of data
Yeah.
that's skewing your results. And without those density measurements, you might never have even noticed it.
Exactly. And maybe this cluster represents customers from a specific geographic region.
Right.
Or customers who use a certain feature of your product that's buggy or confusing. And with that knowledge, now you can go investigate further. You can try to address those underlying issues and potentially improve your churn prediction model by a lot.
I see. So it's not just about improving the overall accuracy of the model, but also about making it more nuanced and sensitive to the different patterns within the data.
Precisely moving from a one-size-fits-all approach to something much more targeted and personalized.
Okay, that makes sense. But let's zoom out for a second and think about the bigger picture here.
Sure.
Why is this idea of measuring data suddenly gaining so much traction?
Yeah.
Is it just about building better models?
I think it's bigger than that. I think it reflects a deeper shift in how we think about AI as a whole.
Okay.
We're realizing that data isn't just this passive input to our models.
Yeah.
It's this dynamic force that shapes the behavior and the impact of those models.
So by measuring data, we're not just measuring the fuel for AI, we're measuring the potential consequences of AI.
Exactly. And that's where things get really interesting and potentially challenging.
Right, because as we've seen with things like facial recognition and predictive policing,
Right.
AI systems can perpetuate and even amplify existing societal biases if we're not careful.
Yeah, absolutely.
So how does data measurement fit into this broader conversation about responsible and ethical AI?
Right.
Does it help or does it make things worse?
I think it has the potential to do both.
Okay.
So on the one hand, data measurement can help us identify and mitigate biases in our data sets.
Okay.
So for example, by measuring the diversity of our data,
Right.
we can help ensure that our models are being trained on a representative sample of the population.
Makes sense. But I can also see how data measurement could be misused to create a false sense of objectivity or fairness.
Absolutely. Just because we can quantify something doesn't mean we fully understand its nuances or implications.
Right.
And if we rely too heavily on metrics without really thinking critically,
Yeah.
we can end up reinforcing existing power structures or creating new forms of discrimination.
So it's not enough to just measure data. We need to measure it responsibly.
Exactly. But what does that actually look like in practice?
Well, I think it starts with acknowledging that data measurement isn't this neutral, purely technical endeavor.
Okay.
The choices we make from what we measure to how we interpret the results
Right.
are shaped by our values, our assumptions, our understanding of the world.
So we need to be more transparent about those choices and their potential consequences.
Exactly. And we need to engage in this broader societal conversation
Yeah.
about how we want to use AI and what role data measurement should play in ensuring that it's developed and deployed in a way that benefits everyone.
That's a tall order, but it's an important one.
It is.
It seems like data measurement is both this powerful tool and this double-edged sword.
Yeah.
It can help us build better, more ethical AI systems, but it also requires us to be incredibly mindful of its limitations and potential for misuse.
Couldn't agree more. And as AI becomes more and more integrated into every aspect of our lives,
Yeah.
the stakes are only going to get higher. Okay, so we've explored the why of data measurement. Its potential to improve models, drive better decisions, and contribute to a more responsible AI ecosystem.
Yeah.
But this journey isn't over.
Not at all.
We've laid the groundwork, but now it's time to look beyond the present and explore what lies ahead for data measurement.
Absolutely.
So for those of you who are curious about the future of this rapidly evolving field, join us for the final part of our deep dive. We'll delve into the frontiers of data measurement and the exciting challenges and opportunities that lie ahead. Welcome back to the final part of our deep dive into data measurement. We covered a lot of ground, from defining what it is to why it matters for building AI systems that are both responsible and effective.
Yeah, and now I think it's time to look ahead.
Yeah.
What are the frontiers of data measurement? What are the big questions that are still out there? What's next?
Exactly. So what are data measurement researchers kind of struggling with these days? What are the most exciting challenges that they're working on?
Well, one of the biggest challenges is developing new data measurement techniques for data types that are more complex and emerging.
Okay.
We touched on this a little bit earlier with multimodal data, but the reality is that a lot of real-world data doesn't fit neatly into the categories of text images or numbers that we're used to working with.
So give us some examples. What kind of weird data is pushing the boundaries of data measurement?
So think about time series data.
Okay.
With all the sensors and the Internet of Things, we're collecting all this data from heart rate monitors to traffic cameras to weather stations.
Yeah.
But how do we measure the characteristics of these dynamic streams of data?
Right. It's not like we can just take a snapshot and apply the same measures that we use for static data sets.
Exactly. Time adds a whole new layer of complexity.
Yeah.
We need new measures that can capture things like trends, seasonality, correlations over time. So, for example, instead of just measuring the average temperature over a year, we might want to measure how temperature fluctuates throughout the day or how it changes from season to season.
I see. So it's about moving beyond static snapshots and capturing the dynamic nature of the data.
Right.
What other weird data types are out there challenging our current measurement toolbox?
Well, another one that's really interesting and challenging is graph data.
Okay.
So think of things like social networks, transportation systems, biological pathways. All of these can be represented as graphs where you have nodes that represent entities and edges that represent relationships between them.
So in a social network, the nodes would be people and the edges would be friendships or connections.
Exactly. But how do we measure the characteristics of a graph?
Yeah.
How do we quantify things like the connectivity of the network, the influence of certain nodes, or the presence of communities or clusters?
Right.
Traditional data measurements don't really work here.
Yeah, we need specialized measures that can capture the unique, topological and relational properties of these complex systems.
Exactly. And understanding those properties can be super valuable.
Right.
Like identifying influential nodes in a social network could help us understand how information spreads or target interventions more effectively.
Okay.
In a biological network, it might help us uncover new drug targets or disease pathways.
It feels like every new data type we encounter opens up a whole new world of possibilities and challenges for data measurement.
It absolutely does. And this is really just the tip of the iceberg. I mean, as we continue to generate and collect more and more data from sources we haven't even thought of yet, the need for these innovative data measurement techniques is only going to become more important.
So we've talked about the challenges of measuring complex data types. What other frontiers are there in data measurement research? What are the big unanswered questions that you're most excited about?
Well, one area that I'm really interested in is the development of data measurements that can capture the meaning or the semantics of the data.
Okay.
Most existing measurements focus on structural or statistical properties, but they don't necessarily tell us anything about the underlying concepts or relationships that the data represents.
So we might know that two words frequently appear together, but that doesn't necessarily mean that they have a meaningful relationship.
Exactly. We need data measurements that can go beyond those surface level associations and capture the semantic relationships between data points.
Okay.
So, for example, instead of just measuring the co-occurrence of words, we could measure their semantic similarity or their relationship in a knowledge graph.
That makes sense. It's about moving from simply analyzing patterns to actually understanding what those patterns mean.
Precisely. And this kind of semantic data measurement could have huge implications for everything from natural language understanding to knowledge discovery to personalized recommendations.
Yeah, as we move towards more sophisticated AI systems that can truly understand and reason about the world, semantic data measurement is going to be essential.
Right. It's like we're trying to teach machines not just to read the words, but to actually understand the story.
That's a great analogy. And it really highlights the fact that data measurement isn't just a technical challenge, it's a fundamental challenge in AI research.
Yeah.
The tools we develop to understand our data will ultimately shape the kinds of AI systems that we can build.
Absolutely.
So as we wrap up our deep dive into data measurement, let's leave our listeners with a final thought to ponder. What's the one big question you'd like them to take away from this conversation?
Well, we've talked about all these different ways to measure data distance, density, diversity, tendency association. But what new measurements can we imagine? What aspects of data are we not capturing yet, especially as we move into these new fields like reinforcement learning or when we're dealing with complex multimodal data? I think that's the question that's going to drive the next wave of innovation in data measurement.
It's a question that challenges us to think beyond the tools we have today and imagine new ways of understanding and quantifying the data that's shaping our world.
And ultimately, the answers to these questions will not only advance our understanding of data, but will also shape the future of AI itself.
Well, on that note, we'll wrap up our deep dive into the fascinating and always evolving world of data measurement. We hope you enjoyed this exploration, and we encourage you to keep digging into this field until next time.